Hi, my name is Julia Silge and I'm a data scientist and software engineer at RStudio. Today in this screencast, we're going to use this week's Tidy Tuesday dataset on working papers published by the National Bureau of Economic Research. And we're going to train a multi-class predictive model. We're going to use regularized regression because it's a good fit for the kind of predictors we have, which are text predictors. Oftentimes when we look at examples of how to get started with predictive modeling, even with text, they're very often like a two-class problem. How, yes, no, kind of binary classification. But in this example, instead, we're going to work on multi-class classification. If we have these research papers, how do we tell the category that they belong in?
All right, let's get started with this data set of National Bureau of Economic Research working papers. So there are a lot of different little data sets here, which is kind of fun and interesting because so the papers are in one data set, the authors are in another, the paper programs are another, which is kind of interesting, and then we can learn about the programs here. And they all have these variables that lets us link them up, so we can use joins to link them up. For example, I can take the paper programs and I can left join on the programs here. So the paper programs this is an identifier for the paper. This is the program here. And then here the program tells us the name of the program and then the program category here. So if I join those up, I have for every paper here that is in a program, I have the description of the program, and then I can see like how many different categories there are. Program category, like this. So some are not in programs. And then we have some in finance, macroeconomics, and microeconomics. If I left join one more time to the papers like this, I now have when it was published. It looks like these go back to back to the 70s, and a title, a text, a bit of text. So what I think I want to do is I want to look at these three categories, and I want to see if I can connect the title to these three categories. In fact, I want to train a predictive model to be able to see what words in the title can we use those words in the title to predict if it's a finance paper, a microeconomics paper, or a macroeconomics paper. Maybe I'll keep year in there as well and see if year helps make it more predictive or more accurate there. So let's say papers joined. Let's call this here. And then let's say papers joined count program category, like this. So here we get that same result here. I might, since I'm not really, this is pretty interesting, these descriptions, but there's many more levels of those. So let's do a distinct here on paper, program category, year, and title. So let's just keep those things. So now what I have in my data set are for every paper identifier, what category is it in, when was it published, and what's the title. And actually, while I'm here, not is NA program category, because I am going to just be looking at the ones that have a category, because that's the thing that I'm going to try to predict. Notice that this is not binary classification, yes, no. Instead, we have three categories. So we're going to be doing multi-class classification here. Before I get started on the model, I'm going to just do one exploratory plot. I'm going to use Let's get this up so it's up a little bit here. I'm going to use tidy text, and then I'm going to use tidy low, which stands for tidy log odds. And let me load both of those. So I'm going to use the bind log odds function to compute and then bind on the posterior log odds ratio. So this is going to be a weighted log odds. It uses, the default here is to use an empirical Bayes approach, where you use the counts that you have of how many things you have, and to weight. So if you count something a lot of times, you're more sure about the log odds. And if you only count things a little bit of times, you're less sure. So you pull it more towards, just sort of the average there here. So it's nice in a it's a nice approach in a situation like this when you have words. So let's take the papers. I'm going to tokenize and tidy this. So word title like this. So now I have, instead of variation across household in the rate of something, variation across household in the rate of inflation, like this. I am going to count program category word. Let me throw a sort equals true here so we can see, the most common words are the and of, although we're starting to see evidence here in microeconomics. Apparently they talk about evidence. And now what we're going to do is we're going to say bind log odds. So the first, we pipe in the data, then the set of things that we're looking at a feature, which in our case is words, and we're comparing across a set. We're comparing features across a set, and here our set are these different program categories. So program category word, and our count is n. So let's save this as title log odds. So this is the weighted log odds of the words and the titles of these papers, these National Bureau of Economic Research papers. So so now I've got that. Let's look at it here. So we have these words that are used a lot here at the top. I can arrange to look at the highest log odds ratio words. So trade, monetary exchange for macroeconomics, Medicaid for micro, risk asset. Let's make a visualization because this will be easier to see visually. So let's group by program category. Let's take a slice by log odds. Let's take the top 10 of the highest log odds weighted words, and then let's ungroup. And now let's pipe that straight into a plot. Let's put log odds weighted on the x-axis, word on the y-axis. Let's do fill equals program category like this. Let's make a bar plot. I don't need that legend for the color. And facet wrap. And we're going to facet wrap by the program category. Like this. All right. So I need to do scales equals free y. Let's say labs x equals, let's see, I could say like log odds weighted like this, y equals null like that. All right, that's pretty good. And now let's just reorder the words. So let's say fact reorder. And let's reorder by log odds weighted like that. All right, nice. Okay, so in finance, the highest log odds words, so the words that that we are more likely to see coming from finance papers that are from the category of finance: risk, asset, stock, corporate. We are more likely to see these stop words. I didn't remove stop words. Notice that they look like they might be informative. Equity, financial. In macro or international, macroeconomic or international category papers: trade, monetary, exchange, international, rate, policy, inflation. And in micro, Medicaid, health, child, obesity, adult, medical, teachers, drugs, Medicare. So these do look like they're papers that are about pretty different things, at least when you look at the words that are the most different between them. So this is a little bit of some exploratory data analysis, and now we can get started on building our model. So this kind of information is the kind of information that we're hoping our model can incorporate in learning a difference. So let's load the Tidy Models framework, and let's start out by spending our data budget. So we have quite a bit of data here, I believe. Yeah, that's a nice amount, especially for a text data set, I think. So we'll take papers, oh my gosh, joined, initial, so I'm going to make a initial split of papers joined, and I'm going to do stratified resampling on our outcome. Which is the category. So this is not something that we have two levels of. We're going to do binary classification, but instead this is going to be multi-class classification, where we have three things that we are going to be being able to tell the difference between, which is, a harder problem. So we're going to split our data in, let's call this NBER folds. We are going to split our data into training and testing, and then we're taking our training data and we're going to create cross-validation folds. And I'm going to do stratified resampling here as well. Okay, so this part of modeling is what you want to think about as like spending your data budget. You have a certain amount of data. You're going to hold some of it back here for testing at the end. We are not going to use that for choosing a model, tuning a model, training a model. We're holding that much back for just assessing how our model does at the end. Then our training data is what we're going to be using for training, tuning, choosing, everything we're going to use that goes into the model here. And it is, and that's what goes into making our folds, our cross-validation folds. And so we have 10 cross-validation folds, and each one of these folds, this data will be used for fitting a model, and this data will be used for assessing a model during each of these folds. Okay. So now let's talk about feature engineering, because this is what our input here is. This text that we have here. And I think I'm going to use year as well, because when we're doing modeling, we can combine text data as input with other kinds of data, like numeric data that we have here. So I am going to I'm going to load the text recipes package. It's an add-on package for recipes. I'm going to say I have a recipe here. I'm going to predict program category with year plus title. So these are the two things. And then my data here that I'm going to give it is the training data. So what this is being used here for during feature engineering is saying, hey, here is what the data is like. It has, this is what the columns are called. This is what the data types are like and whatnot. So then I'm going to go through a basic, I'm going to go through a basic sort of nice default for text analysis for an NLP model. I'm going to tokenize. I'm just going to use sort of a default tokenization here. I'm going to use a token filter, meaning and the way I'm going to do is I'm going to say how many tokens am I going to keep. This is pretty short text and it's pretty limited vocabulary. It's all about economic concepts, so I'm going to keep this quite small. Only 200, and maybe I could go to 500. I don't know. You could experiment with something like that. And then I am going to use TF-IDF. So the reason I'm going to use that is so TF-IDF is like a nice normalized statistic for how important is one of these words, how unique is one of these words to the document that you're looking at. And the other thing I think I might do here, let me just remind myself, program. This is pretty imbalanced. So I think what I'm going to do is I'm going to go to the Themis package, which has add-on steps for dealing with class imbalance. And I'm just going to take the sort of what you might call brute force approach, and I'm just going to downsample because there's quite a bit of data here. So I am going to throw away the enough of the larger categories so that they match the smaller category. And so when I go through my folds, different examples are going to be thrown away each time to get down to the smaller number. So let's call this my recipe for these working papers, like so. And so this is all about feature engineering, data preprocessing. I haven't really talked about what model I'm going to do yet, but this here, I'm deciding how am I going to handle this text that I have. The year is just still there. If you want to look and see how this is going, the first thing that you'll do is you'll prep it. So what prep does is it goes to say, the tokenization and the downsampling, the computing TF-IDF, and it says, what do I need to do from the training data? What do I need to know to be able to apply that to any other data? And then if you want to see what does it look like, we can get the training data back out that after pre-processing by saying new data equals null. So this just gets the training data back out. And this is what our training data looks like. Notice that it is now much smaller than the training data actually is. And that is because we, threw away a bunch of examples. And we have category here. This is the thing we're going to predict. We have year. That's one of our predictors. And then all these TF-IDF columns are other predictors. So we have words like American, at, benefits, as, bank, asset. And so we've got 200 of those. And there are a lot of zeros and every once in a while a value. So that is the way that text data works. You end up with these really sparse matrices, that sometimes we can take advantage of when we do computations. Okay, so first, how you're going to spend your data budget. Next, feature engineering, and then next, our model. So for some kind of models, they can just natively handle multi-class classification. XGBoost is one of these. Ranger Random Forest is one of these. What I want to use here is a kind of model that works quite well often with text, and that's regularized regression. So for regularized regression, multinom reg, when you go to multi-class, we have to use a different, it doesn't natively handle it as well. So what we are going to do is we're going to predict multi-class data using the multinomial distribution with GLMNet or GLMNet, however you prefer to pronounce it. I am neutral on that issue. You can say that however you want. So we're going to predict this multi-class data here. The reason that, so we can't just use just regular, logistic reg here because it cannot natively handle it. So we're going to tune the regularization, like how regularized should this model be, and I'm going to use a lasso model here. with mixture equals 1. So if we go here to the GlimNet page, a mixture of 1 corresponds to a lasso model. And what this means is it's going to be able to send some predictors all the way to 0. And that's good for us because we have so many predictors, so many words. So it's going to be able to find, when it fits the model, how many of the, like which of these words are not important, and we can just, not keep in our model. So let us, I don't think we need to set the mode. Well, I'll just do it. Just to show classification. This is a classification model, but not with 2 outcomes, with 3. And the engine, I do need to set, I guess it's the default, but actually I may not need to do that either. Okay, and so this is, let's call this multi-spec. So this is my my model specification. So this is a specification for a multi-class problem, because I have 3 things I'm trying to predict here, not 2. So multinomial regression. All right, so let's put it together. It's time to put it together. So I am going to put it together in a workflow. I'm going to put in my preprocessor. No. My recipe. And I'm going to put in my model. Like that. So let's call this my workflow here. So right now, this workflow has a preprocessor recipe and a multi-class GlimNet model. So these things are all in here together. I can't just fit it because I don't know the right value for penalty yet. I could just put in some value like 0.01 or something like this, but it turns out this is a hyperparameter of this model. We don't know ahead of time what the right value for regularization is for any given data set. So instead of just picking a value here, instead I am going to tune that value, and I'm going to use my folds that I made, and I'm going to fit a whole bunch of different values to all of these folds and pick what the right one is. So I'm going to make a regular grid of for penalty. This is a little small. Let's I think we're changing this actually. Let's just go with that. And how many does that make? Okay, I need more than that. Let's say levels equals like 20. That should still go pretty fast. And so this is a grid of values that I'm going to try. Like that. I took a bit of control here because the penalty range goes very small. Like, oh, you only want a teeny tiny bit of regularization, and I'm pretty sure I want more regularization than that. I don't want to go to like down to teeny tiny values. I want to stay bigger than that in this example, partly so it will run faster and in this example. Okay, now it's time for tuning. So I have everything I need now for tuning. I'm going to use parallel processing. I am going to set a seed because we got some randomness here. And then I'm going to use tune grid. Just straightforward because there's nothing really, I don't think I would gain by doing anything fancier than this. So I'm going to tune my workflow. I'm going to tune it with my folds, and then I'm going to tune it on my grid. And let's call, whoops, I need a comma. And let us call this my result. All right, and let's do this. So this, I think, should go pretty quickly. So this is so what's happening is for my workflow, which has a preprocessor and a model. I am, for every one of these, no, I'm sorry, for every fold, whoops. Oh, I have to say grid. Whoopsie daisy. Let me try that again because it's on the other side of the dot. So I have to say that I'm using that grid. So let's try that again. Okay, so for every, where I lost my place. Okay, so for every resample on this number of observations, I am going to fit 20 different values of penalty. And then on the other side, I am going to evaluate with that. So fit 20, evaluate each one, fit 20, evaluate the one. And then I have metrics for each one of those. So for example, I can see how this all turned out. So I can look at it visually like this. And we can see that, the accuracy and the ROC are like flat, 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 and then they just like drop down as we take out many, many of the features as the regularization gets big. And we can look at what which of the values for the regularization turned out best here. So notice that this says the ROC is computed in a different way because we have 3 different outcomes. So, and if I said, for example, metric equals accuracy like this, it's multi-class accuracy here, and we have these penalties are the ones that have the best results, like so. So so these are now the penalties that give us the best results there. Okay, so we have now built and tuned a model, and now it's time for us to choose which one we want to use and evaluate it. So one thing about regularized models is that we could, so let's say I have this result. I could do something like select best. And I could say metric equals ROC AUC like this. And that would give me the best, as it says in the name, the best one. But often with regularized models, we say, well, I don't want the numerically best one. I want one that is about that good, but is simpler. Because you say, well, I don't, I don't really believe that there is that much difference between this numerically best one and a simpler model that will take out more terms. So there's these different sort of heuristics and rules for how you're going to choose a simpler model, and one of them is this like one standard error within the best value. So we can say here, let's say we want to choose it by descending penalty here. And so it gives us a higher penalty where the penalty is taking out more of the results here. And so it gives us some information here about like the best and how, where the bound is and whatnot. So let's call that let's call that our final penalty. Like this is the penalty we're going to use. And often like a reason to use regularized models is so that you can, make a choice like that. So this is our final penalty. And then we can use that. So if we have our workflow, we can finalize our workflow with that final penalty like that. So before it used to say penalty equals tune, and now we're putting in that penalty that we chose using this rule about how to choose a penalty. And now we'll use Lastfit. So Lastfit is a function. Let's call this final result. And I will print it out here. So what Lastfit does is notice that what I give it is the split. The split contains the information about both the training and the testing. So what Lastfit does is it fits to the training set and evaluates on the test set. It really makes it easy to have good practices on the fact that we don't ever evaluate on the whole training set, because that will just fool us as to how good we're expecting to do later. Instead, we want to evaluate on the test set. So now we can do things on, so what final result here gives us is a tibble, and it gives us things like, here's how much data went into it, here's metrics, predictions, and whatnot. So the metrics, if we can say collect metrics on the final result, that gives us, these are the metrics on the testing data, not the training data. And so what this tells us here, so the ROC is computed for all three classes here. The accuracy, notice that you might see that and be like, oh my gosh, that's low. So accuracy for multi-class problems is often low, and that's because it is harder to get something right when you have many buckets to put things in. Just like numerically, that is how it works out. It's much harder. It's a much harder problem to get things right when you have multiple options, multiple buckets to put things in. So that is something to keep in mind. We can also look at the predictions. So these predictions are also on the training set. If you look, oh, that printed out ugly. There we go. If you look at the number, this is the number of things we had in the testing set, if you remember. And what we have here is a predicted probability for all of these different categories. We have the real value down here, and we can plop that into a confusion matrix. So let's say program category. So that's the true value, and then we can say the predicted class, which would be whatever it had the highest predicted value for here. So we got a nice little printout there, or we can make a plot. Whoops. And this here, so when we trained it, remember we balanced the classes. So it was trained on data that had equal numbers of these three, but now we're looking at the testing data. And so we are looking at the proportions as they exist in the real data set. So microeconomics, it did an okay job recognizing that. Finance, I would say the same in terms of how successful our model was at finding that. The macro, a little harder. It was a little harder for it finding the macroeconomics papers. But you can see here how successful on the testing data this model was at identifying these three kinds of models. So the area here of these blocks tells us how many numbers fall into each of those buckets. And the truth is down here on the x-axis, prediction is over here on the y-axis. So lots, and again, we can see lots more microeconomics papers than finance papers, for example. The last kind of plot we might want to make here is an ROC curve. So let's do this again. And let's, what does that look like? Okay, because to do an ROC curve, I need to say the truth, program category, and then I need all three of the predicted probability. So pred finance to pred micro, like that. So this is going to give me three ROC curves. There they are. I don't like them being I don't like them plotted like that. 1 minus specificity, sensitivity, activity. I like them being all together so I can see them better, like one on top of each other. So I'm going to need that line, slope equals one line. Let's make it gray, and let's make it dotted, dashed, I guess. And then let's put those on. I think it looks best if they're like geom path. And let's make them a little bit thick and a little bit transparent because they're going to be on top of each other. And we don't need that label. Oh yeah, and let's do chord equals fixed, like that. Okay. Okay. This is what I wanted to see. There we go. So finance and micro are very close, especially up here in this threshold. And macro, it was harder to find. So that agrees, you know, this makes sense given the confusion matrix that we saw. So that's that all makes sense, right, with each other. All right, so pretty nice. Okay, so the last thing I want to talk about is making new predictions. So if we have this final result thing here, you can call extract workflow on it. And what this gets out is, let's call it, I'm going to call it final workflow here. So what this is a thing that you can call predict on it. You could also, for example, write it out as a RDS like this. Like you can save it somewhere, like write it like it's a, you know, if you ever like written a CSV file, you can write it out as an RDS file and then load it back in later into another session if you need to make predictions. This is the thing you would want to do that with, is this workflow. This is what you predict with. So we can now predict on the final workflow. You know, let's show how to do it with the test data. So like whatever, I don't know. You know, so here we get the predicted probabilities for this particular, so this is involuntary terminations under explicit and implicit, blah, blah, blah. And it's from 1981. And okay, so it was actually a micro paper, but in this particular case, our highest probability is that it is a macro paper. We can predict for, you know, we can make up our data. Let's put it in a table. Like this. Let's say it's so I think our two predictors are year and title. So let's say it's something that was published this year, a working paper that was published this year, and gosh, let me real briefly again make this plot again. Okay. So let's look at some of those words on that finance thing. So let's make a paper that's called Pricing Models for Corporate Responsibility. I don't know. Okay, so it said it was finance. If we say type equals prob here, we can see how sure it was. So finance is quite a bit higher than micro and macro there. So let's, you know, so this is how we make predictions on new things. We put in new data here. So if instead of these, like if you look at those words that are in micro, so if we say like teacher health and Medicaid expansion. I don't know. People are talking about that. You can see it definitely thought it was a micro paper, you know, and left over there. So this is how you make predictions with a final object, and apparently how I decide to write economics working papers.
All right, we did it. We used this data on the titles and the year as well of these research papers, and we predicted the category of them. It was a multi-class predictive model using this text data and year data. And so we had to, we used the kind of metrics that we used were different. How we dealt with ROC curves at the end was different. But many of the kinds of things we normally do during predictive models do extend as well. And at the end, we walk through how we would predict with our final trained model. So I hope this was helpful, and I'll see you next time.